You have a table of 11,000 finished jobs and a model that is right about as often as your best guess was 2 months ago. You tune it for a week. You lose 3 afternoons to feature ideas that each buy you nothing. And the whole time you carry a suspicion you have no way to test, that your plateau is not in your data at all, it is in the shape of the machine you reached for without thinking. So you ask the room, and the room has its answer ready. Everybody knows which library to grab. It has won more tabular competitions than every rival combined, it is the default in 1,000 starter notebooks, and your colleagues will nod when you say the name. That is a recommendation, not the explanation. But what is it actually doing differently? You do not know, which leaves you with no idea when it will quietly let you down. Hold that question, and we will come back to it right at the end, where what waits is duller and far more useful than the leaderboards suggest. What should you listen for? Here is the shape of the answer. Something in this method is doing work that has almost nothing to do with statistics, and everything to do with how fast you can find out you were wrong, and how little that costs you. And you should care even if you never enter a competition in your life. The same library sits in production behind fraud scores, ad ranking, delivery estimates, and the churn models somebody on your team inherited. So which of its knobs are actually load-bearing? Not knowing means you are tuning by folklore, and folklore is expensive to debug at 3 in the morning while a customer waits. Let us make this concrete and keep it for the whole episode. Cairn is the small service a 2-person team runs to answer exactly one question: will this maintenance job overrun the estimate we quoted? 11,000 finished jobs, 20 features each, the truth already known for every row. They want to be less wrong by Friday, and they have no appetite whatsoever for a research project. Ask what this famous method is, and the easy answer arrives instantly. It is called boosting, only better. Simple. And that does sound like it settles something. But we should really avoid ranking 2 methods before saying what either of them does. Better at what, exactly, and measured how? Cairn has no use for a winner. Cairn needs to know which machine matches the shape of its problem. Both machines in this story assemble a committee out of one weak model, usually a tree so shallow it is barely useful alone. The entire difference is a single design choice, and you can state it in one sentence. Is each member of the committee allowed to see what the previous members got wrong? Answer no and we call it bagging. Answer yes and we call it boosting. Everything else, all the papers and all the flags, follows from that fork. Now the word that does the real work here. Gradient boosting means you never fit the next tree to your data at all. You fit it to the derivative of your own error. Write down how wrong you currently are, in a form that can be differentiated, and the slope of that quantity tells every new tree where to shove. That is what we call gradient boosting, the term Friedman published, and it predates the library you are arguing about by more than a decade. So here is the loop, and it is shorter than the vocabulary stacked on top of it. Start with one constant prediction, the average, which is wrong for everybody. Then measure the slope of the loss at every row, fit a shallow tree to those slopes, add a shrunken version of that tree to your running total, and repeat. And after 300 rounds? You hold 300 trees, each one apologizing for the ones before it. Notice what is missing from that recipe. Knowing which way to shove is not the same as knowing how far, and Friedman's version handles the distance by searching for a step length. This library asks a second question instead: how sharply does the slope itself change? That second derivative, the curvature, is Newton's method arriving quietly inside a tree library, because curvature is what tells each step how far to go. Nobody puts that on the marketing page. Once you have both numbers, the best value for a leaf stops being a search and becomes arithmetic. Add up the slopes of every row that lands in that leaf and call it G. Add up the curvatures and call it H. The optimal weight is minus G divided by H plus a penalty you choose. Divide by curvature, and a leaf sitting where the loss bends sharply takes a small careful step, while a leaf on a flat stretch is handed a large one. Here is my favorite consequence, and it is the step where the design turns genuinely strange. The score for a candidate split is G squared over H plus penalty for each side, minus that same quantity for the parent, and then minus a flat charge for the privilege of owning one more leaf. Why square G? Squaring rewards agreement inside a leaf. And the flat charge? Subtracted unconditionally, every time. So a split that truly reduces your error can still score below 0, and the tree declines to make it. Sit with that for a second, because it is lovely. Pruning is not a tidying pass bolted on after the tree is grown. It is inside the score, so the tree never grows the branch in the first place. Two hyperparameters you probably copied off a blog post, the leaf penalty and the leaf charge, are the two halves of that arithmetic. They are not vague regularization vibes. They are terms in one equation you can write on a napkin. Now the part that should not work at all. Every tree you add gets multiplied by a small number, often 1/10, before it joins the total. You are deliberately throwing away 9/10 of the correction you just computed. Do that and what happens? You need roughly 10 times as many rounds, so the whole procedure is slower and measurably better. Weakening each individual step improves the finished machine, and nobody has proven exactly why. The same trick shows up in a second place. Each tree is shown a random subset of your columns, perhaps 12 of your 20 features, so no single dominant feature gets to steer every member of the committee. Friedman had that trick for bagging long before boosting borrowed it, which is worth saying plainly. A great deal of what you call one algorithm is a careful assembly of other people's parts. Then there is a detail that sounds like housekeeping and is not. Your columns have holes in them, and most methods make you fill those holes with a mean or a zero, which is you inventing data and then training on your own invention. This one learns, for every split, which direction a missing row should travel, and it learns that direction from the loss. Absence stops being something you patch and becomes something the model gets to use. There is a second reason practitioners reach for this on messy tables, and it depends on something you probably have. Your columns are on wildly different scales, dollars beside days beside a count of parts. A method that measures distance would need you to normalize all of that first. This one splits on thresholds inside a single column at a time, so scale never enters the arithmetic. You still require clean labels, but you do not require tidy features, and that difference alone saves Cairn a week. And it never tries every threshold, because on a wide table that would be hopeless. It summarizes each column into a few hundred candidate cut points, weighted by curvature so the regions the loss actually cares about get finer resolution. What does that cost you? A sliver of accuracy on every split. In exchange you finish 300 rounds while the exact method is still grinding through its first tree, and that exchange is the whole story. So how much of the win is arithmetic and how much is memory layout? You can separate them, and the answer is uncomfortable. Then build the same process step by step on a naive row by row layout, because that is how you isolate it. It computes the identical model, just far slower. The predictions do not change at all. Only the number of experiments you can afford before dinner changes. That is a strange thing to call one algorithmic advance, and it is the honest description of what happened. So what actually won those competitions? Here is the unglamorous answer. Almost none of the statistics above is new. The gradient idea is Friedman's, the column sampling is Bryman's, the shrinkage is older than both. What was new is that somebody laid the data out in compressed column blocks sized to fit in cache, sorted each column once and reused that order for every tree, then spread the work across your cores. A round that took minutes took seconds. Note, that gap between the idea and the usable implementation is where most of the value in applied machine learning actually sits, and it is the least glamorous thing anyone will tell you. Friedman's paper describes the mechanism completely. It took another decade of unglamorous engineering before you could run that mechanism 300 times before lunch. Which of those two contributions do you honestly think moved the field further? Do not take my word for any of this, because the experiment is small enough to run today. Take your own table and fit 300 rounds at a rate of 1/10, then record the score. Then set the rate to 1 and use 30 rounds, so the total correction is the same size. If shrinkage were merely a slower road to the same destination, those two would land together. Measure it yourself. They will not. Now for what this cannot do, and the first limit is the one that catches people out. A tree can only ever predict a value it has already seen. Feed Cairn a job larger than anything in its 11,000 rows and it will not extrapolate beyond the range it was trained on. What does it hand back instead? The closest thing it knows, and it sounds confident doing it. A plain straight line, which you dismissed in week 1, handles that case correctly. And the trade-off you will actually feel is tuning. A random forest has perhaps 2 settings that matter and forgives you the rest. This has depth, rate, rounds, 2 penalties, subsample fractions, and a minimum child weight, and they interact, so moving one changes the best value of the others. So is the accuracy free? Not remotely. You pay for it in search, which is exactly why the engineering mattered more than the mathematics. Now, how much should you trust a number this thing hands you? Less than the accuracy score suggests, and the honest limit is worth stating. Its confidence depends on the density of similar rows nearby, and it will happily report a tight estimate for a job that resembles nothing in its history. Calibration may still be poor even when ranking is excellent, so if you plan to threshold on the raw score, be cautious, measure the calibration separately rather than assuming the ranking carried it. In practice, start at depth 6, rate 1/10, 300 rounds with early stopping, and change one thing per run. Notice that this advice is folklore too. It was measured on somebody else's data, and as far as anyone knows it has never been shown to transfer to yours. Treat it as a starting corner of the search, never as a setting that has been justified for your problem. There is also a deeper thing nobody has proven. We can show that each round lowers the training loss. Why a machine carrying thousands of leaves does not simply memorize your 11,000 rows, and instead generalizes beautifully on data it never saw, is not settled theory. The received wisdom is that the shrinkage and the sampling and the leaf charge together act like a budget on complexity. That is a plausible account. It is not a proof. Caveat: none of this makes the method a default you can stop thinking about, and the limit is worth stating plainly. On text or images it will lose badly to a network that understands structure. On a genuinely linear relationship it will lose to a straight line with 3 parameters. Which of those you need depends on your problem, not on a scoreboard. What it is unusually good at is precisely Can's situation, a wide table of mixed, messy, hand-entered columns where nobody knows the functional form. And what does one of these models cost you to keep alive? People underestimate this consistently. 300 trees is 300 structures to serialize, version, and load on every deploy, and a model that must be explained to a regulator is riskier than one you can write as a line of arithmetic. In practice, that trade-off is the one teams regret. Your straight line has 3 parameters and a printable formula. If somebody will have to defend a single decision in a meeting, that plain model may not be worth abandoning. So, back to that question you have been holding since the opening. What did this method actually change? The answer is that it made being wrong cheap. Every part of it, the curvature, the sketch, the cache blocks, the sorted columns, buys the same currency, more experiments per afternoon. Going forward, that is the sentence worth keeping. The winners on those leaderboards were rarely the people with the best prior. They were the people who tested 40 hypotheses while everybody else tested 4. Caveat: the way to find out whether any of this matters for your table is not to read another benchmark. Fit the plain straight line first and write its score on a sticky note. Then fit this and compare. If the gap is 2%, you have bought 2% of accuracy for a permanent increase in operational complexity, and only you can say whether the trade is worth making on your own table. Most teams never run that comparison at all, and then go on to quote somebody else's leaderboard instead of their own measurement. Which leaves the decision with you, and it is a smaller decision than the hype around it suggests. Ask yourself what a wrong estimate actually costs you, whether anybody will have to explain a single prediction to one angry customer, and how many honest experiments you can afford before Friday. If that last number is dozens, this machine will reward you richly. If it is 2, your afternoon is better spent on your data. Your call either way, and now you can answer it from the mechanism instead of the scoreboard.